If I told you that growing older, and even the onset of cancer isn't actually caused by your body breaking down, but by your body's software perfectly executing the wrong code, would you believe me?
I mean, it sounds like science fiction, right? But that paradigm shift is profound, and it is entirely reshaping the consensus in molecular biology right now.
Right, because I really want you, the listener, to completely forget the old mechanical metaphors we always use for aging. Forget the idea of a car rusting in the driveway or like the gears of a clock slowly wearing down.
Yeah, that's exactly what the science we are looking at today suggests. Viewing aging as this inevitable stochastic entropy, like our biological hardware just slowly falling apart, is actually entirely backward.
Which is wild. So what we are actually dealing with is a reversible software glitch.
Exactly. Your DNA hardware is largely fine. It's the instructions telling that hardware how to operate that get corrupted over time.
Well, welcome to this deep dive into the source material. I'm your host, and today our mission is to explore this phenomenon called DNA methylation instability, or DMI.
It's a fascinating topic. We're going to decode the exact mechanisms of how your cellular software degrades.
Yeah, and then we are going to unpack the futuristic science that's actively trying to reboot that software. We're talking everything from literal telomere rivers that pipe youth between cells to precision epigenetic editing tools that honestly make CRISPR look like a blunt instrument.
So to understand how to fix this software, we first have to understand what the architecture of the software actually is. The sources focus on a very specific baseline.
Right. They mapped the human genome and pinpointed exactly 31,744 specific loci.
Yes, exactly, 31,744. They call these stable methylation sites, or SMSs, and they derive this pristine map by looking at the cells of healthy 18-year-olds.
Which makes sense as a baseline, and I found the location of these sites really telling. They aren't just like scattered randomly across the genome, are they?
No, not at all. They're heavily clustered around the on switches, the promoters of our most essential housekeeping and repair genes. The odds ratio for them being in CPG islands is like 13.8.
That's massive. Think of these 31,744 SMSs like the protected system 32 files on your computer's operating system. They govern DNA repair and the cell cycle checkpoints that literally stop cells from dividing out of control.
That's a great analogy. And in a youthful state, these sites are completely unmethylated. Being unmethylated means the chromatin is physically open and accessible.
So the cell can actively read those critical system files.
Right. But keeping those files open and unmethylated takes a massive amount of continuous biochemical work. The cell employs this whole dedicated workforce to manage the code.
You have the writers, right?
Yeah, enzymes like DNMT3A that add chemical methyl marks to the DNA to silence certain regions. And balancing them, you have the erasers.
Like the TET2 enzymes.
Exactly. TT2 continuously removes rogue methyl marks to keep those vital system files open and readable.
So it's like a constant tug of war. The writers are trying to close things off, and the erasers are fighting to keep the critical files open?
Yes, and the core of DNA methylation instability, the actual system crash we call aging, happens when this delicate balance gets thrown off.
The writers start putting chemical tags where they shouldn't, right?
Yeah.
And those protected system files get methylated, and the critical genes just get silenced.
That's the glitch. And the sources identified 3 primary saboteurs that initiate this catastrophic crash. The first saboteur is genetic.
Okay, so we're talking about somatic mutations here.
Right, alterations you acquire over your lifetime, not the ones you were born with. These typically occur in the stem cells inside your bone marrow, a condition known as clonal hematopoiesis of indeterminate potential.
Or a CHIP, for sure.
Yes, CHIP. And these mutations strike the very epigenetic modifiers we just mentioned, like the DNMT3A writer or the TET2 eraser.
And the speed at which these mutated cells take over is honestly alarming. I was reading that if a stem cell acquires a mutation in DNMT3A, that specific mutated clone will grow at a rate of about 5% per year.
Which is fast, but it gets worse.
Right.
If the mutation hits a splicing factor called SRSF2, those rogue clones can grow at over 50% per year.
Wait, 50%? That's insane. They would just completely hijack the bone marrow.
They absolutely do. They dominate the microenvironment because the mutation alters their epigenetic software to give them an aggressive survival advantage over healthy blood cells.
No.
They refuse to die and just continually divide.
Wow. Okay, so genetics is the first saboteur. What's the second?
The second driver of this instability is metabolic, and it centers on how our cells process basic nutrients through the one-carbon cycle.
Let me push back on this metabolic aspect for a second because the mechanism here is wild. The text points to a specific ratio between two molecules, SAM and SAH.
Right.
Are you telling me that a lack of basic dietary nutrients like things like vitamin B12, folate, or choline can actually starve my cells of this SAM molecule and directly cause my DNA's software to corrupt?
The biochemistry supports exactly that. So SAM, or S-adenosylmethionine, is the universal methyl donor in the body. It is the physical chemical that the writer enzymes use to place methyl marks on DNA.
Okay, so they need it to do their job.
Exactly.
Huh.
And when a writer enzyme takes the methyl group from SAM and attaches it to the genome, the leftover molecule becomes SAH, S-adenosylhomocysteine.
So running out of SAM is essentially like a printer running out of ink.
Yes, but from what the sources show, the resulting SAH doesn't just act as an empty ink cartridge. It actively jams the printer.
Oh.
Yeah, it acts as an inhibitor that physically blocks the writers from doing their job properly elsewhere.
So that SAM to SAH ratio is really the master indicator of your cell's methylation capacity.
Absolutely. If your diet lacks the folate or B12 necessary to recycle that SAH back into methionine to make fresh SAM, the ratio plummets.
The inhibitor takes over.
Right. The fidelity of your Cy4 maintenance fails, and the methylation patterns begin to drift completely randomly.
Okay, so we have genetic mutations warping the writers and metabolic starvation jamming the machinery. What is the third saboteur?
Chronic inflammation. Persistent inflammatory states, whether that's from obesity, aging, or chronic infections, keep the immune system constantly activated.
And that involves neutrophils, right?
Yes, neutrophils flood the tissues and release an enzyme called myeloperoxidase, or MPO.
Which produces hypochlorous acid, which, chemically speaking, is essentially bleach. I mean, we're dumping bleach on our DNA.
Basically, yes, it creates severe oxidative stress, which physically modifies the bases of your DNA.
Yeah.
It creates these specific structural lesions known as 8-oxo-DG.
8-oxo-DG. Okay, so think about this mechanically. When a cell divides, a maintenance enzyme called DNMT1 runs along the DNA to copy the healthy, unmethylated patterns onto the new cell, right?
Right, it's driving along the strand.
But when it hits one of these oxidative 8-oxo-DG lesions sitting inside a protected site, it acts like a physical pothole. The enzyme hits the roadblock and literally falls off the DNA strand.
It just detaches. And because of that, the newly divided cell simply doesn't get its epigenetic code copied correctly.
So the inflammation is quite literally tearing up the roads that the maintenance crew needs to drive on. That's brutal.
It is. And to compound the damage, the hypochlorous acid also oxidizes the active sites of the maintenance enzymes themselves, rendering them useless.
While simultaneously draining the cell's methionine pool, it's a highly coordinated multi-front attack on the epigenome.
Exactly.
So if inflammation is constantly putting potholes in our code and our maintenance enzymes are starved and mutated, how does a cell go from having a few molecular potholes to actually forming a tumor or causing heart failure? Like, what bridges the gap between a software error and actual clinical disease?
The bridge is the unintended silencing of sentinel genes. The sources highlight a specific gene called BASP1 as the prime example of this.
BASP1?
Yeah. Normally, BASP1 acts as a powerful tumor suppressor. If a cell begins to act radically, showing signs of malignant transformation, BASP1 triggers apoptosis.
It commands the dangerous cell to self-destruct to protect the rest of the body. So it's the cellular emergency alarm system.
That's a perfect way to look at it.
Yeah.
But the DNA methylation instability we've been talking about specifically targets this alarm.
Oh, wow.
The software drift hypermethylates the BASP1 promoter. It essentially blankets the gene's on switch in chemical tags until the alarm is completely muted.
So once BASP1 is offline, those rogue mutated cells we discussed earlier, the ones expanding at 50% a year, they lose their self-destruct mechanism.
They do. They evade the immune system, they outcompete their healthy neighbors, and eventually they organize into malignancies or drive arterial plaque formation.
It's like the burglars are cutting the alarm system before they rob the house.
Exactly.
And this metric of software corruption, DMI, is already being used in the real world, isn't it? The text mentions it's a better predictor of cardiovascular mortality than standard genetic screening.
It is, because it captures the actual downstream phenotypic drift. A standard genetic test might just look for a specific inherited risk allele.
Right, something you're born with.
Right. But tracking DMI allows doctors to measure the active, hidden expansion of pro-inflammatory cells that are currently driving atherosclerosis and heart failure.
That's so much more practical.
Yeah, and one clinical study of patients in cardiogenic shock, tracking their DMI levels reliably stratified them into distinct risk groups with a high statistical significance. The p-value was 0.01. It identified who was truly in danger before traditional physiological signs even appeared.
And the application in leukemia patients blew my mind. In chronic myeloid leukemia, or CML, doctors are tracking a specific metric called the DMI-CML score.
Yes, and the fascinating thing about that score is that it is entirely dynamic. It actually decreases when a patient is put on targeted drug therapies.
So unlike a hard-coded genetic mutation, which is permanently etched into the DNA, the epigenetic state is highly fluid.
Completely fluid. By tracking the DMI-CML metric at diagnosis, doctors can measure the tumor's adaptability. High baseline instability means the cancer is highly evolvable and likely to develop drug resistance.
But a decreasing score shows the therapy is actively stabilizing the software. It provides a real-time window into the behavior of the disease. So if this instability is fluid, and we can track it decreasing in leukemia patients responding to drugs, that begs a massive question. Can we actively reverse it in healthy tissue that has simply aged? Like, can we de-age the software?
The sources detail exactly how researchers are doing this, starting with epigenetic biological clocks and the restoration of vision.
Oh, this part was fascinating.
Scientists have identified specific multi-omic aging genes that serve as incredibly accurate biomarkers of our biological age. And the single most precise predictor of chronological age across these epigenetic clocks is a gene called ELOVL2.
Let's follow the mechanism on this one. As we age, our software drifts and DMI slowly hypermethylates and silences that ELOVL2 gene. In a youthful, active state, what does that gene actually produce?
It produces an enzyme responsible for elongating specific polyunsaturated fatty acids. Crucially, it creates a lipid product known as 24.5N3.
Okay, 24.5 and 3.
Right, which serves as a vital precursor for DHA, an essential component for maintaining healthy retinas.
So the software glitch turns off the gene stops making the enzyme, and the eye stops receiving this crucial lipid.
Yes. And that chain reaction leads directly to age-related vision decline, losing contrast sensitivity and the ability to see in the dark.
But the researchers bypassed the broken software entirely. They asked what would happen if they just directly supplied the missing biological output.
They synthesized that specific 24.5N3 lipid and injected it directly into the systems of aging mice.
So wait, they didn't even fix the gene itself, they just provided the missing output, and the mice literally regained their visual contrast and dark adaptation.
That's exactly what happened.
That's wild. That implies the biological decline isn't permanently broken hardware, it's just paused software. If you feed the system the correct outputs, it boots back up.
It serves as a brilliant proof of concept. But, bypassing a silenced gene with an injection is really only a patch. The ultimate goal is systematically fixing the software itself to protect the entire organism.
Right. Fixing eyes by bypassing the software is one thing, but fixing the code system-wide is the holy grail. Let's get into the pharmacological toolkit designed to counter DMI.
This is where it gets really exciting.
Yeah. The first major player is something millions of people have in their medicine cabinets right now, GLP-1 receptor agonists. They are famous for weight loss, but the text frames them as a metabolic shield for the epigenome.
They trigger a profound molecular reorganization that goes far beyond appetite suppression. GLP-1 arrays activate a very specific cellular pathway known as the AMPK-TT2-1433 phosphoswitch.
I love how the mechanics of this play out. So GLP-1s aren't just slowing down digestion, they're essentially dispatching a molecular security detail, the energy-sensing enzyme AMPK, to put a bulletproof vest on our epigenome's most important maintenance worker, the TT2 eraser enzyme.
That bulletproof vest being the 1433 protein, that is an incredibly accurate way to visualize it. Once TET2 is shielded by those proteins, it cannot be destroyed by the cell's natural turnover processes. It stays active, continuously erasing those rogue methyl marks and keeping the system files open.
Which is exactly what we want.
Exactly. Additionally, the GLP-1 arrays cause the sustained phosphorylation of a mediator protein called MED14. This locks the cell's stress response enhancers into an active state.
And the clinical outcomes of this epigenetic armoring are staggering. Patients on GLP-1 RAs showed a 35.7% reduction in their risk of developing colorectal cancer compared to patients taking aspirin.
And it gets better. The specific drug liraglutide hit an astounding 56.4% reduction.
We are talking about preventing more than half of major cancers just by stabilizing the software. That's unbelievable.
It really highlights that cancer is often an epigenetic disease first. But what happens if the software is already heavily corrupted and locked down? How do we pry it open without breaking the cell?
Right, because prevention is one thing, but reversal is another.
Exactly. That requires highly selective histone deacetylase, or HDAC, inhibitors.
Histones are the spools that our DNA winds around, right? And HDACs tighten that spooling, turning genes off. Inhibiting them forces the spool to unwind and opens the DNA back up.
You got it. But the early drugs for this, like vorinostat, were incredibly blunt instruments.
Yeah, they just kind of hit everything.
Right. Vorinostat inhibited multiple classes of HDACs indiscriminately. This caused severe off-target effects, most notably HERG toxicity, which leads to fatal cardiac arrhythmias.
Yeah, you cannot treat aging with a drug that stops the heart.
Definitely not. So the newer generation of drugs, like sanacrizumab A, solves this through extreme precision.
The source's note is 3,600 times more selective for just the HDAC2 isoform. It's like selectively loosening a single tangled thread without unspooling the whole sweater.
By targeting only HDAC2, sanacrizumab A safely restores a highly specific histone mark called H4K16A.
H4K16A, okay.
Yeah, and this mark is absolutely essential for recruiting DNA repair machinery to sites of damage, and it does this without triggering any of the dangerous cardiac side effects seen in older drugs.
Okay, so we can shield the healthy cells with GLP-1s, and we can gently unwind the tangled code with selective HDAC inhibitors. But what do we do about the senescent cells?
The zombie cells.
Yeah. These zombie cells have stopped dividing but refuse to die, and they just sit around spewing the exact inflammation that causes the epigenetic potholes we talked about earlier.
The traditional approach was to hunt down and kill these zombie cells using senolytics. But a newer strategy detailed in the sources is called senorreverse.
Senorreverse.
Yeah. Instead of destroying the cells, which can cause its own tissue damage, scientists are using stable microRNA mimics, specifically miR302b, to reprogram them.
So instead of nuking the zombie cells, we are essentially flipping a switch. We're suppressing a cell cycle inhibitor called P21 to just force them back to work.
Exactly. It promotes chromatin opening and forces the cell back into a healthy, functional cycle. In animal models, this senorreverse strategy increased overall lifespan by up to 22.1%.
Wow.
And crucially, it did so completely safely with zero increase in tumor incidence.
That's huge.
It is.
Yeah.
And concurrent with this, the arsenal includes microenvironment defenders compounds like 4-aminotempo and DMPO, which patrol the tissues and physically trap those inflammatory bleach-like radicals before they can ever reach the DNA to form potholes.
Okay, so we are waking up the zombie cells and sweeping the inflammatory roadblocks off the streets. But we have to talk about the most sci-fi concept in the entire source stack.
Telomere rivers.
Yes, telomere rivers. I was reading the section and I couldn't quite wrap my head around it. The text makes it sound like rejuvenated immune cells are literally building physical pipelines to pump youth into older cells. Is that an actual physical structure, or is it just chemical signaling?
It is a literal physical transfer of genetic material.
No way.
Yes. Researchers discovered that rejuvenated CD4-positive T cells can form extracellular vesicles and nanotube networks, these rivers that connect to aging neighbor cells.
Okay.
Through these networks, the T cells actively transport their own telomeric DNA into the older cells, physically extending the recipient's telomeres and extending their lifespan.
They are essentially sharing their own cellular battery power. That is mind-blowing.
It is, but there's a catch. As the immune system ages, an inhibitory protein complex builds up that physically blocks these rivers from forming.
Ah, of course.
So the pharmacological intervention here is a new class of drugs called DOS disruptors. Molecules like DOS36L are designed to dismantle these suppressive complexes, unblocking the networks and allowing the telomere rivers to flow freely across the tissue, triggering massive systemic rejuvenation.
If the idea of cellular rivers piping telomeres around the body wasn't wild enough, we have to touch on the ultimate code rewriting tool.
Right.
Everyone knows about CRISPR. It won the Nobel Prize. It gets all the headlines for gene editing. But the sources focus heavily on a different system called TIGR-TAZ. Why are researchers looking past CRISPR for fixing our software glitches?
Well, TIGR-TAZ, which is derived from bacteriophages, offers several massive mechanical advantages over CRISPR's Cas9 system. The first is simply its physical footprint,
It's smaller.
much smaller. Tiger Tez is only about a quarter the size of the Cas9 protein. And in the world of genetic engineering, smaller is always better because it is vastly easier to package and deliver into living human cells.
The size makes total sense. But the sources also emphasize that Tiger Tez is PAM independent. CRISPR needs a specific barcode, the PAM sequence, to sit right next to the target DNA to know where to cut right.
Correct.
That means there are entire sections of the genome that CRISPR is just blind to, so Tiger Tez can just read the whole genome without needing that barcode.
That is the crucial differentiator. Because it does not require a PAM sequence, Tigers can be programmed to target literally any coordinate in the entire genome.
Wow.
Furthermore, it utilizes a 36-nucleotide double-stranded guide RNA. This gives it an unprecedented level of precision. When Tiger makes a cut, it doesn't just shear the DNA bluntly. It creates staggered cuts with an 8-nucleotide overhang, often referred to as sticky ends.
Oh, I've heard of that. Those sticky ends are vital because they allow scientists to seamlessly paste in new epigenetic instructions without relying on the cell's own error-prone repair mechanisms to fix a blunt break.
Exactly.
So we could theoretically use Tiger-Taz to navigate directly to that BASP1 alarm system we talked about earlier, snip away the hypermethylation, and manually turn the tumor suppressor back on.
Yes, it represents the absolute pinnacle of precision epigenetic medicine. We are no longer just slowing the decay. We have the theoretical blueprints to actively rewrite the corrupted code back to its youthful baseline.
That is incredible. Let's pull all of this together. We started by dismantling the idea that aging is just biological rusting. We explored how our healthy software relies on 31,744 perfectly pristine genetic switches.
Right.
And we saw how genetic mutations, metabolic starvation from a broken one-carbon cycle, and inflammatory potholes corrupt that software, silencing our internal bodyguards and opening the door for disease.
But the defining takeaway is that we are not powerless against it. We can track this instability dynamically in the clinic, and we are developing an astonishing arsenal to reverse it.
From GLP-1s putting bulletproof vests on our eraser enzymes, to highly selective HDAC inhibitors gently unwinding the code, to waking up zombie cells, unblocking telomere rivers, and using Tiger-Tez to rewrite the code with total precision.
Whole new frontier.
It really is. And this brings me to a final thought I want to leave you, the listener, with today. As we've seen from these sources, your biological age is increasingly looking like a malleable software state. We are rapidly approaching a reality where reversing the methylation of a gene to turn back the clock on your cells isn't science fiction, it's just engineering. So how does that fundamentally change the way you live your life today? I mean, if your chronological age hits 80, but your epigenetic age could be medically reset to 30.
Well, it completely shatters how we think about human identity. It reshapes the concept of retirement, the traditional arc of a career, and really the structure of society. If the rust is just a glitch and the glitch can be patched, your life is no longer defined by how much time you have left. It is entirely about how well you manage your software. Think about that next time you look in the mirror. Your hardware is fine. We are just waiting to install the update.